Manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box of maximum volume? Surface area, the area of the outside part or uppermost layer of something. That is the definition. You're wondering about that. All right, so at least it'll give you a sense of how to come about that formula. So an attempt to draw is about to happen. Just sit back, relax, and judge. Okay. So square base, obviously. I'm going cross-eyed. It's happening. I need it back. All right. Oh. I had to power through it. Oh.
That takes so much effort.
Once my retina folded in upon itself, like I couldn't see it anymore. Like these two panels started looking like they were going the other way, and now they're going the other way again. Oh, all right, hold on. I lost it. I lost it. All right, it's back. It's back. All right. I'll shade in the part that I intend to be the top. Yeah, it was tough. I had the top in like 5 different places before I drew that in. Had it like projecting out at me, which was kind of cool to think about, but not a visually accurate kind of thing. All right, so we want the surface area to be 108, so I'll make a note of that. We're talking about dimensions that will produce a box of max volume. We know it's a square base, so that's good news. All right, even though it doesn't quite look like it. Square enough on the base. So the 2 dimensions for the base would be the same. I'll call those x. The height we'll call y. All right, so volume would be, length times width times height, so x squared y. All right. So if we could swap out a variable here, ideally the y, it's going to make our lives a lot easier. In order to do that, I need a model that represents the area of the figure, right, excluding the top. All right, so the 4 side panels are all going to have the same area because they have the same dimensions. So area would be xy. If you just look at a single panel, that front panel, for example, has a dimension of x by y, right? It's congruent to the back panel, so same dimension. Side panel, x by y also. So we have a congruent side opposite of that. In total, we have 4 of those xy panels. The base itself has dimensions of x by x, so x squared. All right. So since we know that the area is 108, I can say 108 equals 4xy plus x squared. We're looking to optimize volume, all right? There is an application for this. It just doesn't seem like it would be an overly useful one, because it's like every math class that you've taken, this question or some variation of it has come up at some point. But really, it's getting to the idea of maximizing your resources. Right, so if you have a certain amount of material, if you could use those or use that material in such a way to maximize whatever it is that you want, productivity, volume in this case, temperature, if you're talking about a heating device, then you're probably applying this concept. Right, so in this case, we're talking about a rectangular prism, but we got to, like I said before, we got to start somewhere. Anyway, I need to use this to support my main equation. My main equation is volume because that's the thing we're looking to maximize. All right, maximum volume is my key term, if you will. All right, so that's the one I'm going to be looking to differentiate. right? So I need to solve my area equation for y in terms of x. So I'm going to subtract an x squared from both sides. So 108 minus x squared. Then I'll divide by the 4x. And that'll be equal to y. So I could swap out the y for that. Now, since we're going to be taking the derivative, it's probably in our best interest to simplify this a little bit. Otherwise, you'd have to take the derivative of that. And that would involve product rule, quotient rule. I mean, the only thing it wouldn't have would be chain rule, I guess, but it's still not something we're overly eager to do. All right, so let's clean it up a little bit. I know that this x will go into that x squared x times. So v would be equal to, I'll run the x through the top, 108x minus x cubed over 4. But still has kind of a quotient rule feel to it, so let me clean it up further. Break up the fraction. We'd be looking at a 27x minus 1/4 x cubed. All right, so just basically dividing each part of the numerator by 4. All right. Makes it a power rule type of situation. So I could differentiate. V prime would be 27 minus 3/4 x squared. I need to find the critical values, identify extrema from there. All right, may consider factoring out a 3, then multiplying by 4. So essentially multiply the whole thing by 4/3 to clear out that denominator. So 0 would be equal to, if we divide 27 by 3, it's 9, times 4 is 36, minus x squared. So x squared would be equal to 36. X would be equal to 6 or negative 6, but we would ditch the negative 6 because we're talking about dimensions of a geometric figure. All right.
This isn't about the function. I'm just in a dire situation where my calculator is about to die. Can I plug it in?
Yeah, in the back. The wire should be hanging. It's a self-destruct. It's like, if I can't have this information, nobody can. So it really did die. Like, that is the definition of it. Like say a prayer for it and everything. So we get x equals 6. Now, what we were dealing with here was a cubic function originally. Cubic functions take on a variety of forms. If you just draw a sketch of what a cubic graph would look like, especially in this case it would be a negative cubic. I'm going to go purple for that. You're talking about, let me just scooch over a little bit more. Something that could look conceivably like this. In which case you're looking at a value that would have, precisely. It would have a minimum first and then a maximum if it were going to have two critical values. So that could be enough justification for you to say that the 6 is going to be the relative max. All right, just based on your knowledge of cubic functions. All right, you've discovered that there are two critical values. Now, if you go further and you find out that the point of inflection happens to be the same as one of those critical values, then that could make things a little confusing. You'd start looking for a mistake. But this is, I mean, if you know what a cubic graph looks like, these would coincide with the critical values. The negative one would happen before the positive one. So then logically you could assume that the 6 would represent the relative max, right? But that's not going to work in all cases because, again, we're going to come across functions that when you see the equation, you don't automatically know what the graph is going to look like. So we go to the second derivative test. So I need v double prime. Sorry. So when I take v double prime, I'm working off of, oh, you could see it actually. It was perfectly fine the way it was. We're working off the first derivative. The constant goes away. We're looking at negative 3/2 x.
Why do we need the second derivative?
One sec. Second derivative test for Extrema will verify whether or not it's definitely a relative max or min. So if I find v double prime, and this is in lieu of making a sign chart. We'd rather do this than a sign chart because sign charts suck. I mean, there's a place for them. Don't get me wrong, but I don't know where that place is. So you plug in the 6, and really, again, for a second derivative test, we're just looking for the type of number, so not what the number is. If I plug in a 6, I'm going to get a negative number. Therefore, 6 gives a relative max. All right? Because, again, this is talking about, not that part of it, this whole part of it is talking about an interval that's concave down. All right, if it's concave down and you have an extreme value on that interval, it must be a max. All right, so just have to make sure we answer the question that was being asked. What dimensions will produce a box? All right, so take my area formula, because that was my known expression. A equals 4xy plus x squared. All right, other ways you could do it, but this is probably the most analytic way. We know that the area has to be 108, and we just figured out what x is. So 108 minus 36 is what, 72? Equals 24y. All right, well, 3 days, right? 24 hours by 3 days is 72 hours. That's how I remember that. It's one of those obscure things that only works in like 2 instances all year long. But I don't have to worry about it, so it's kind of nice. So y would be equal to 3. So we're talking about dimensions being 6 units, inches, by 6 inches by 3 inches. Those are the dimensions that would produce a box with the most volume, excluding the cover. They exclude the cover on purpose, because if the cover was included, then it would always be a cube. So you would just take the cube root of whatever the surface area was, and those would be your 3 dimensions. So it's not really a calculus question when that happens.
Can you explain again why if you take the second derivative of 6 and it's a negative number, it means that it's a round max?
So if you take the second derivative, any sign that you get from that indicates concavity. So if it's a negative sign, it's concave down. And so if you have an extreme value on an interval that's concave down, it must be on the high side, because a critical value is where the slope goes to 0. So it must represent a turning point, but specifically on the high side, because of the nature of the function. There would be no way for the graph to belly down in order to grab a minimum while also being concave down. It would have to be concave up in order for that to happen. So if we know it's an extreme value, so a critical value, and we know it's in an interval where it's concave down, it must be a max. If I plug this in, I would get a positive number. That would be an interval where it's concave up, indicating that it would be a minimum.
So you keep saying interval, but you're only plugging in one number.
Right, because it's happening, that number is only relative to this particular interval of the graph. So I'm plugging that number as a representative of that interval. Okay? So it's kind of like the relevant piece of the sign chart without doing the entire sign chart.
Okay. If it came out as a relative min in like a real world problem, would that like not work for plugging it in?
Well, if we came up with a relative min, you'd be like, oh crap, yeah, this problem doesn't work. And if you just base your life's work around that, it's like, all right, back to it doesn't work. Thanks for the grant money. I guess I'll be looking for another job because the whole reason you hired me was to
go back to school.
My premise is faulty. It's all over. So. Yeah.
Go back to college, get an
Liberal arts, baby. Go for it. You have a future in it. So a box with a square base, open and an open top. It's always an open top again. I'm very, very concerned about boxes. I was so concerned that boxes would be like when I became a teacher, because I've never really known anything other than swinging a mop and being a teacher, like in terms of jobs. Swinging a mop. Yeah, that's an expression for janitorial services.
Oh, I thought you
So-
meant like karate.
No. No, I was part of a Broadway musical. My mop was my prop. Yeah, no, it's mopping the floor, cleaning toilets and things like that. So that was high school and college, and then after that, a little student teaching, and then pretty much this. So when I started teaching, it seemed like there was problem after problem related to these boxes. And I actually legitimately thought for a period of time that there was some industry out there where like a bunch of math nerds were going to just design different boxes. And I thought it would be the craziest thing if that happened. And then Amazon happened. And exactly, and I'm like looking at all these different shapes of boxes with like different bubble tapes, and I'm like, there really is a place. Like these box people are out there. It's crazy.
But like we would say like we must have a volume of 32,000 cubic centimeters.
Precisely.
engineering and then making boxes.
Yeah, I mean, I just kind of imagine like there's some Amazon person like in the back room doing calculations, being like, all right, we need box 32 alpha. Bring it in, because we have a shipment of pens, rubber bands, and staples. They're not going to fit into anything else. I've done all the calculations. You can double check my math, but they're not going to fit into anything other than 32 alpha. Like,
Really interesting because Amazon usually like packages their boxes really well.
they're pretty well.
Thinking about it.
Amazon must have a lot of different box sizes.
And they're
Yeah,
bags.
but the reality is it's probably like,
They have a box size associated with the product.
and you have like one thing of nail polish remover in there. Yeah.
And they came in an Amazon box. They were perfectly like.
They also, like I've ordered
It is
small
amazing.
things, they put them in
Thank
big
you.
boxes and
Yeah.
throw them a lot of bubbles.
I ordered a vial of gallium.
Yeah.
And like
Yeah.
a vial of gallium is captured.
No.
And you're like,
Oh, it's that metal, that melting point is like 80 degrees, so like you hold it in your hand and it melts. Yeah, yeah. So I ordered one of those, and it was like that big, but it came in like a box. So confused.
Because somebody was looking at it being like, this might be a hazardous substance. Let's just let's get a package of daylights out of it.
With the holiday box scam device.
No.
We just looked at it with the glitter. Did you see that one?
No.
The NASA engineer.
Oh wait,
made,
can we
like-
watch that in law?
Yeah.
Yeah.
This like guy noticed people stealing his packages on his porch, and
Put
he made
glitter
like
bombs in them.
he-
And
yeah.
we recorded it.
He made a fake like Apple speaker box, so it looked like it was like a new Apple product, and then
So
when
people
people
would
opened
steal it.
it would
No,
like
people would
spray
have to
glitter
steal
everywhere.
That's kind of funny. I thought it was like a real bomb that was somehow made out of
No.
glitter.
So like he would leave
Like
nice
glitter shrapnel, like tearing up their
he would
faces
leave,
and stuff.
nice
Like,
products in like a parking garage, and then if you stole it, it would explode and
With
cover you in
cameras.
glitter. But it was
Yeah.
funny because he recorded.
I want to do
It was really Sure.
Imagine a bomb that says fire.
That's what happened, but not really. It was fine. No one got hurt.
Yeah, that's exactly.
It was
Tragic death by glitter. Like that's not my good. That can't be my obituary. I'm gonna go on a straight and narrow from now on. All right, so yeah, the box has a square base, of course, and an open top. So same picture basically. Now this time the volume is 32,000. So basically they're telling us that some information about the volume, and we need to minimize the amount of material used. AKA we have to minimize surface area. So it's the opposite, right? So volume would still be x squared y. So 32,000 would be equal to x squared y. The area model, still what it was before, 4xy plus x squared. All right, it's just the area function is the one that we're going to minimize. So that's the one where I want to swap out a variable. I want to pull that y and replace it with, in this case, it'll be 32,000 over x squared. So a equals 4x times 32,000 squared plus x squared. All right, and again, same story as the last problem. We have to differentiate this, so we want to clean it up first. So x would go into x squared, x times, but this time on the bottom. So a would be equal to 128,000 x to the negative first. 64,000 doubled, right? And then I'm just taking the x that was on the bottom, swinging it to the top, making it a negative exponent, just so I could take advantage of my power rule. All right. Differentiate. A prime would be equal to negative 128,000 x to the negative second plus, looks like 2x. Then once you do that, you might want to go back to a more convenient form. If you want, you can also clear it out by multiplying by x squared, but you may not necessarily see that, at least in the early going. So you could write it as negative 128,000 over, come on, you can do it. You don't want to do it? Fine, I'll do it again. X squared plus 2x. Either form is fine. If you write it like this, when you set it equal to 0, we can clear out the x squared on the bottom. Thusly, multiply through with an x squared, and we'll get 0 equals negative 128,000 plus 2x cubed. We have a common factor of 2. We could drop that, divide it out. 0 would be equal to negative 64,000 plus x squared, x cubed, sorry. Solve the cubic. It's cubic in a binomial form, which is great, so I could just add the 64,000 to both sides. And then take the cube root of both sides. And so I get x equals 40. All right, so I have that. I need to verify that that's going to give me what I need, because we need this to give us a minimum on the area. Just verifying, yep, minimize the amount of material cost. So again, in lieu of doing a sign chart, just take the second derivative which is going to be 256,000 x to the negative third plus 2, and evaluate it for the critical value. I'll just make a note, that's my critical value, a double prime of 40. And just take note of what type of number that would be. Right? So a negative exponent doesn't make a number negative, it just makes it into a fraction. So a positive number in a fraction form is still going to be a positive number, a positive fraction. So positive quantity added to another positive quantity, result is going to be positive. All right, so therefore we're looking at something that's concave up, and that tells us that 40 gives a relative min. All right, so 32,000, if I remember correctly, was equal to x squared y. If I want the y value to go with it, we do 32,000 equals 40 squared y. All right, so y would be equal to 32,000 over, well, 40 squared is 1,600. Drop a couple of zeros. Talking about 20. All right, so then I just have to go back for a sec here and find the units. Centimeters. All right, so dimensions are what we were looking for. So it would be 40 by 40 by 20. 40 centimeters by 40 centimeters by 20. And there it is.